Here's our last example from section 4.5 on optimization problems. And in this one, we are looking for an optimal path. So our scenario here says that a lifeguard needs to get to a person 100 feet downstream on the opposite shore of a 50-foot wide river as fast as possible. What optimal path should the lifeguard take if they can swim 5 feet per second and run 15 feet per second? So, first things first here, if you are in this situation, if you are the lifeguard or the person giving help, don't waste your time doing this optimization problem. The optimal path is whatever gets you there as fast as you can in that instant. You go help that person. You don't take 15 minutes doing math and then help them. So just wanted to make that very clear that this is not what you would actually do, but it can give us an idea of, hey, what maybe should we expect to do in this type of scenario? All right, so let's sketch a picture as we do. We need a river. Okay, it's a very straight river. And it's flowing this way, so this direction will be downstream. Just arbitrarily, your picture might look a little different. And let's say our lifeguard is currently right here. And our person having an issue is 100 feet downstream on the opposite shore. So they are over here. I'll put P for person. And they say, help. Okay, so there's the person going, help me. Okay, so they are 100 feet downstream from the lifeguard. So that tells us this dimension right here is 100 feet. And the river is 50 feet wide. So that tells us this dimension right here, 50 feet. Okay. Now we can see some different scenarios of what could go on here. All right. There's different paths that the lifeguard can take. Let's just sketch a few of them. So one path the lifeguard could take is they could go straight to the person, swimming the whole way. So they're in the river this whole time. So they could do all swimming. Okay. Or they could do the least amount of swimming possible would be to go straight across, land right here, and then run all the way down to the person. Okay, that's another potential path that they could take. Sorry, I dropped my pen there. Or they could do something in between. They could swim part of the distance, land there, let's say, and then run the rest of the way down the shore to get to the person. Okay, so in each one of those, we have a situation where the lifeguard needs to land somewhere on the opposite bank. It's either going to be right across from them, at the person, or somewhere in between. So let's set it up like this. Let's say that the lifeguard is going to swim and then land somewhere that's X feet downstream. And then run the rest of the way. Okay, so X could be like 0 if they land no feet downstream, if they just swim straight across. Okay, X could be 100 feet downstream if they swim the whole way and they cover that whole 100-foot distance. Or X could be somewhere in the middle. And that's the case I'm going to label to help us see it a little clearer. Okay, so this is going to be X feet downstream. And then that remaining distance then between the landing point and the person, that would be the rest of that 100-foot distance along that side of the river. So this is going to be 100 minus X. So actually that running the rest portion is going to be 100 minus X feet. Now, we might also note that there are some boundaries on X, some values that X should lie between. And that would be between 0 and 100 feet. Because the lifeguard probably would not have any advantage in swimming past the person and then running backwards. That would just add extra time to the path. So we don't want them to swim any more than 100 feet downstream. We also don't want them to swim this way in the negative direction back upstream, because that would not be very practical either. Okay, so there's our scenario, and let's write down our goal here. Our goal is to minimize the time it takes for the lifeguard to complete this path. Okay. Now we are going to need an equation for that time. Okay, so let's write down some ideas here. Okay, so equation. We could say that the total time it takes to complete this path is going to be a combination of the lifeguard's time spent swimming plus the time that they spend running. Okay. And we don't necessarily we're not given the times, but we are given a rate at which they can swim and they can run. So we have a rate, we need time. We're going to end up using this equation right here. This is an oldie but a goodie from algebra. D equals RT, distance equals rate times time, the dirt equation. And from that, you can come up with an equation for time if you divide both sides by R. T equals D over R. Okay. So we are going to need to express our time swimming and time running in terms of distance swimming divided by rate of swimming, and then distance running divided by rate of running. Okay, so time, let's look at swimming here. Okay. Well, the distance that our lifeguard swims is going to be this component right here across the river, which currently is not labeled. So let's go ahead and label that. We'll just call that Y. So we'll have Y divided by their rate for swimming, which is 5 feet per second. So Y over 5. And then for the time running, we'll do a similar thing. The distance that they're going to be running is right here along the shore of the river. And we can see that that distance is 100 minus X feet. Okay, so 100 minus X, and divide that by their rate for running, which is 15 feet per second. Okay, So for our total time here, we're going to have a full equation that combines both of those. Our equation, I'm going to call it big T for total time. It's going to equal time swimming, which is y over 5, plus our time running, which is 100 minus x over 15. Okay. Or if you don't like writing the fractions in that way, you could also say this is 1/5 y plus 1/15 times 100 minus x. Okay, that looks pretty good. So notice how, as usual, this right now is an equation of two different variables. We have y and we have x, and we're going to need to fix that. So we need to involve something else that's given in the problem to make our constraint equation that we need to involve. And let's see what we haven't used yet. Okay, so we have definitely used this 100 feet. We've split that into x and 100 minus x. Okay. Now, how about this part of the problem? The fact that the river is 50 feet wide. We haven't really done anything with that yet. So let's focus on that value and see what we can set up. So if you look at that 50 feet, you can see it's straight across the river. We'll say this meets at a 90-degree angle here, because that's the lifeguard swimming straight across. So we've actually got a little right triangle set up right here with our 50 feet, our X and our Y, and that's what we're going to use. Okay, so we're going to take that for the constraint. I'll draw it again down here. Okay, so this is our river width, the 50 feet. Makes a nice little right triangle. Here was X and here was Y. So we can set up a Pythagorean equation for this. X squared plus Y squared equals 50 squared, which would be 2,500. And so you can take that and solve it for either X or Y. Okay, just kind of looking at our time equation here, I think I will choose to solve it for Y because it looks a little easier to plug in. But you should be able to solve for X with the same result. Okay, so I'm getting Y squared equals 2,500 minus X squared. And so Y is going to be the square root of that, 2,500 minus X squared. Okay, so, and okay, this is interesting. Some of you might have been having a little fit during that last couple seconds because I wrote something down wrong. Did you spot what I wrote down wrong? Let's see if you can spot it. I'm seeing it. Yeah, do you see it on YouTube later? Yep, I wrote down the Pythagorean theorem wrong. I was just going default standards here. Let's back that up just a second. Because 50 is not the hypotenuse. Y is the hypotenuse. So the Pythagorean theorem for this should actually be set up as x squared plus 50 squared equals y squared. Okay. Thankfully, I did not get too far with that. I double checked myself before I wrecked myself. So yeah. And so I'm definitely going to solve this for y now because all I have to do is take the square root of both sides. Okay, so y is going to equal the square root of x squared plus 2,500. Okay, that's good. And it is safe to choose the positive square root in this case because y is representing a distance that this lifeguard is swimming across the river. So we would not be saying that they're swimming a negative distance. Go ahead and use that positive square root. Okay, so we're going to take this expression for y and plug it back in to our time equation. Okay, so that means that t is going to equal 1/5 of y, which we just found was x squared plus 2,500, and then plus 1/15 times 100 minus x. And now you can see that our time equation is all in terms of one variable. It's just in terms of x now. So that's going to make it good to take the derivative of this. Okay. Before we take the derivative, I'll do a little rewrite on that radical. This is 1/5 and then x squared plus 2,500 to the 1/2 power. Okay. And might as well distribute this as well. We'll have 100 over 15. Let's divide both of those by 5. That would be 20/3. Okay, 20/3 minus 1/15 x. Okay, that looks better. Well, for taking the derivative at least. Okay, so let's take that derivative. This is going to be t prime dt dx, by the way. And for our first term, we're going to need a little bit of chain rule with our constant multiple out front. So we're going to have 1/5 times, okay, chain rule time, bring down that 1/2, okay, x squared plus 2,500 to the negative 1/2 power, times the derivative of the inside portion. Derivative of x squared plus 2,500 is just 2x. Okay. Now the derivative of 20/3 is 0, so that's gone. And the derivative of 1/15 x is 1/15, so we have minus 1/15 on the end there. Okay, so there's our derivative. Let's clean it up a little bit. One thing you can do is cancel the 1/2 there with the 2 right here. And so we'll have 1/5. I'm going to pull this x out to the front so I don't lose track of it. 1/5 x times x squared plus 2,500 to the negative 1/2 power minus 1/15. Okay. And if we think about what that would look like, let's see, we would have for this first term, just x in a numerator and then 5 and our x squared plus 2,500 to the 1/2 power down there. I'll put it in a square root and minus 1/15. So yeah, I think I'm going to make this into just a single fraction because you've probably seen by this point that does help with finding the critical points. So let's multiply this first expression by 3 and then multiply the second expression by the square root of x squared plus 2,500. That way we can get it all with a common denominator. Okay. So here's our t prime formula here. We're going to have 3x from here and then minus that square root term, minus the square root of x squared plus 2500, all over 15 square root of x squared plus 2500. Okay, there we go. So from that, we can get our critical points. All right, kind of a long process to get to this point. Points, critical points. Anyway, t prime is going to be undefined if the denominator equals 0. So let's set that up. But when you look at that, you would see that that means x squared plus 2500 would have to equal 0, or x squared equals negative 2500, and that is not going to happen. So this is not a real number. Okay, so we're not going to get any critical points from t prime being undefined. So let's focus on where t prime equals 0. So that'd be 3x minus square root x squared plus 2500 equals 0. And let's add that square root to the other side so that we can square both sides of this equation. So square that, square that. We'd have 9x squared equals x squared plus 2500. And then subtract off your x squared. 8x squared equals 2500. And so x squared equals 2500 over 8, meaning that x is going to be a real delight to work with here. All right, x is going to equal the square root of 2500 over 8. And again, we can assume that that's a positive square root in this case, because remember that x is referring to a distance. So that would be root 2500 over root 8. Okay, square root of 2500 is 50. Square root of 8 we can simplify to 2 root 2. Reduce that guy down a little bit. So anyway, my internet cut out for a second there again, but there might be a little jump in the video, but hopefully you're able to piece this together. We were just finding the critical point value where t prime equals 0, and that turned out to be x equals 25 over the square root of 2, which is approximately 17 points. Now let's verify really quickly that this is actually what we want. Okay, let's do a little quick test on t prime. Put our 20 over root 2 right there, approximately 17.7. And we just need to test the derivative on either side of that, which is a little easier said than done in this case. But you would pick some value that's less than 17.7 to plug into your function here. And for instance, think about x equals 0. You'd have 0 minus the square root of 2500 on top, and then divided by 15 square root of 2500 on the bottom. So that would be a negative over a positive. So negative over positive, that gives you a negative first derivative. And then pick something really, really large over on this side, like maybe 100 or even 1,000, any number you'd like to think of. That should give you a positive first derivative there. I'll let you guys verify. So we have a function that is decreasing and then increasing. And so this is actually a minimum, which is what we wanted. We wanted to minimize the time it takes for the lifeguard to get to this person. Gives a minimum total time, check, good. Okay, so we have a minimum total time there. One other thing you might want to do that we have not considered currently is checking the endpoints of our interval, since we did have some. Okay, we noted that X needed to be between 0 and 100, which our critical point 17.7 certainly is. But let's just verify that that time is actually faster than either of these other ones. So yeah, let's test total time. So testing, and I'll make a note that we're looking at our endpoints here, X equals 0, which was to basically swim across and run the rest of the way. Okay, swim across and then mostly run. X equals 100, which was swim straight to the person. Okay. And then our critical point value, we should also calculate the total time for that. 25 over root 2, approximately 17.7. Okay. So let's see what we come up with here. In our time function, t of x, that is, where'd it go? There it is, right here. That's this guy right here. That was in terms of y. Let's go ahead and use our function that's just in terms of x. So I'll put a little star next to this one, showing that we should go on to this next page. Okay. Okay, for our final testing of this. Okay, so t of x, when it was a function of just x alone, that was 1/5 square root of x squared plus 2500, and then plus 1/15 times 100 minus x. Just to verify one last time there. Yes, there it is. Okay, good. Okay, so let's test t of 0. 1/5 0 squared plus 2500 plus 1/15 of 100 minus 0. Okay, square root of 2500 here is 50. So that would be 10 when we do 50 times 1/5, and then plus 100 over 15. All right. And so t of 0 would equal, let's see, 10 plus 20/3 equals 50/3. All right, so 50/3 is, 16 2/3. So t of 0 equals 16 2/3, or we could just say about 16.7 seconds. Okay. Now t of 100, our other endpoint there, okay, is going to be 1/5 times 100 squared plus 2500 underneath our radical, and then 1/15 100 minus x, which is 100. So that second term is just going to be 0 and disappear on us. And so we'd have 1/5 square root of 100, so 10,000 plus 2,500. would be 1/5 square root of 12,500. Okay, and since we're doing approximations here, put that in your calculator, you'll get about 22.4 seconds. So far, the time t of 0 is winning at the moment. Okay, t100 equals approximately 22.4 seconds. All right. And now we need to test our critical points. Because, yeah, if the critical point doesn't give us a time, let's see, less than 16.7 seconds, then x equals 0 would win here. To swim across the river, straight across the river, and then mostly run the rest of the way. Okay, so that's what's winning right now. Let's see. T of 25 over root 2 would be 1/5, and then 25 over root 2, getting squared, plus 2,500 under our square root, plus 1/15, 100 minus 25 over root 2. That's gonna be fun. Okay, this one, you could do a little bit by hand if you wanted to, squaring this radical out, but with this term in there and everything, just let's go ahead and get straight to the approximation. This is approximately 16.1. Okay, so t of 25 over root 2 is approximately equal to 16.1 seconds, making that our winner. That is the fastest path by 0.6 seconds. Okay, so this wins as opposed to that. So our critical point actually does give us the fastest path. So solution for this, a lifeguard should swim approximately, well, let's put the actual answer, swim 25 over root 2, which is approximately 17.7 feet downstream, and then run the remaining distance. Which is, let's see, approximately 82.3 feet to the person. Okay, what a problem. All right, now remember, of course, as I mentioned at the start of the video, if you're in this situation, don't worry about your optimal path. Just get to the person as fast as possible. But notice that swimming part of the way, running part of the way turns out to be the fastest path, closely followed by swimming straight across the river and then running the rest of the way, because this particular lifeguard is a much faster runner than they are swimmer. So this solution could vary for you also. If your running and swimming speeds are different, that would change these values. So this is the optimal solution for this particular lifeguard in this scenario.